Hello starfarers, and welcome back to the Tetra Galaxy Telecast. For this transmission's topic, I will be discussing the gravity of planets in the Metroid franchise. A few calculations have been made based on information known about a couple of the franchise's premier planets, but many more of them remain unknown due to the very limited knowledge surrounding the situation, and even the calculations already done have issues that need to be addressed. That's where I come in. I'll be figuring out as many of the gravities of Metroid's planets as I can using nothing but my wits, my words, and good old reliable numbers. Fair warning, I'll only be covering planets that players can access, so I won't be covering non-playable worlds like Ormine 2, Twin Tabula, Billium, or any planets exclusive to the mangas. And I also won't be going over any non-planet setting like the bottle ship, unless it explicitly helps in finding the gravity of a planet, but we'll get to that later. So turn up your audio master units, get comfy, and maybe grab a snack to keep you company, because this is gonna be a long ride. But without further delay, let's begin. Earth will be the starting point for my calculations for this broadcast, though it will only be used directly to measure two of the planets, Zebes and Talon 4. Now you may be thinking, what's this kid talking about? No Metroid game takes place on Earth! And you'd be correct. However, the Earth's gravity will still be very important for obtaining our desired answers. Why? Because of a very simple equation, G equals m over r squared. For those of you who don't know what that stands for, that's the equation that represents the gravity of Earth. This base form of the equation I showed has three variables, G being gravity, with 1g equaling the gravity of Earth, m being mass, and r squared being the radius squared. So the equation I'll use to get the gravity and g's of Earth for FS176's feature worlds will be g equals mx over me divided by rx over re squared, with 1g being Earth's gravity, mx being the mass of the planet I'm measuring at that point, me being the Earth's mass, rx being the unknown planet's mean radius, and re being the Earth's mean radius. Once I've finished the calculation for the world's gravity compared to Earth, I can multiply the number by Earth's actual gravitational force, which is 9.802 meters per second squared, to get the true gravity of whichever planet I'm currently calculating. So in short, I'll be giving you the gravity in g's of Earth and in meters per second squared. To do this though, I first need to establish Earth's relevant measurements. Fortunately, those stats are fairly well documented. Earth's mass is 5.97219 times 10 to the 24th power, or 5 septillion 972 sextillion 190 quintillion kilograms. Its radius is where we see our first calculation, as to get the mean radius, we need to measure the equatorial radius and polar radius of Earth. You see, Earth isn't a perfect sphere. It's close, but it's actually an irregularly shaped ellipsoid, which means its gravity is ever so slightly different depending on where you are on the globe geographically. So I'll have to find the semi-major and semi-minor axis, and use a mean radius calculator to find the mean radius based off that. Earth's equatorial radius is 6,378.1 kilometers, while its polar radius is 6,356.752 kilometers. Putting this into a mean radius calculator, it gives a mean radius of 6,367.43 kilometers. So with the required parameters of Earth found, I can now compare the Metroid planets to it, and for the sake of consistency, and to ensure no errors occur, I'll be converting all measurements to kilograms and kilometers, since those are the units I have for Earth's mass and radius. I'll also be using a sample weight to show how heavy an object would be on the planet I'm measuring at that point. The sample weight I'll use will be Samus, who's stated to have a weight of 198 pounds in the Super Metroid Player's Guide. I'll then multiply this weight by the gravity of the planet compared to Earth to find what Samus would weigh on the planet. I'll also be covering the planets in chronological order. So with that out of the way, we can finally get to the numbers on our favorite fictitious planet. Many believe that Zebes sits at around 960 Gs due to Wikitroid's old calculation of the planet's gravity. But what if I told you it's even higher than that? I'll explain why Wikitroid's wrong in a bit, but first, I need to establish Zebes' measurements. The mass is given in the observatory room of Metroid Prime, which states the planet has a mass of 4.8 trillion teratons. Converting that to kilograms gives us 4.8 times 10 to the 27th power, or 4 octillion 800 septillion kilograms. Both the equatorial and polar radius are provided by Wikitroid. The equatorial radius is flatly stated to be 5,201.156 kilometers. The polar diameter is stated to be 11,700 kilometers, and since diameter is just radius times 2, the polar radius is easily computed to 5,850 kilometers. Using my old friend the mean radius calculator again, I have measured Zebes to a mean radius of 5,530.66 kilometers. With that, we can now compare its gravity to Earth. Zebes' gravity in G's of Earth will be G equals 4 octillion 800 septillion kilograms over 5 septillion 972 sextillion 190 quintillion kilograms divided by 5,530.66 over 6,367.43 squared, which gives us 803.725.666.11 over 0.8685.859.1299 squared, which can be simplified to 803.725.2666.11 over 0.7544148825, which is equal to 1,065.32485.173 Gs. Multiplying that by 9.802 gives us Zebes' true gravity, which comes out to 10,442.3141967 meters per second. Of course, Zebes isn't a perfect sphere either, having an equatorial radius unequal to its polar radius, so the gravity may be slightly lower or higher depending on where exactly on the planet you are. That said, I wouldn't recommend going there at all. The highest recorded Gs anyone has ever survived was Kenny Brack, who survived a force of 214 Gs during a car crash at the 2003 Texas Motor Speedways. And that was horizontal force, not vertical, and only for a very brief moment. It's established that well-trained humans could survive in constant gravity 5 times that of Earth. And remember, Zebes stands at just over 1,065 Gs, meaning its gravity in Gs is nearly 5 times the highest amount ever survived by a human, and exactly 213 times what any of us could withstand, unless of course you happen to be a non-human viewer, but anyway, I'd stay away from there. Using my sample weight, Samus on Zebes would weigh 198 pounds times 1,065.32485.173, which comes out to a staggering 210,934.32063 pounds, or 105.46716.0322 tons. For reference, the largest animal to ever live on Earth, the blue whale, weighs up to 100 tons, meaning Samus's weight on Zebes is more than that of a blue whale in our oceans. Truly crazy stuff. Before we move on from Zebes, I'd like to bring your attention back to Wikitroid and their calculation for Zebes' gravity, putting it at 955.415.65771 Gs. This is around 100 Gs off from my own calculation, which I have reason to believe is based off one simple error made by Wikitroid during their calculation, using the polar radius for Zebes and Earth, rather than using their mean radii, giving a radius of 5,850 kilometers for Zebes and 6,378.1 kilometers for the Earth, making Rx over Re squared 0.84125776.123, rather than the number I got of 0.7544148825, which results in the improper calculation, which is 803.75083.724 divided by 0.84125776.123, which totals 955.415657699 Gs. Wikitroid claims their number is around 954 Gs, whereas I put their calc at just over 955, but I'll chalk that up to a rounding difference, as they most likely stopped at around the hundredths place for a rounder estimate, which I chose not to do. This isn't meant to be a slight against Wikitroid or its writers. They do a great job covering most Metroid content, and their numbers were only slightly off. The point of this was just to show the minor differences between my work and Wikitroid's, and how easy it is to mess up calculations like these. But enough of that rabble. It's time to make our next planet fall. and bear with me the rest of the way, because it just gets more and more difficult from here. Talon 4 is also fairly easy to get the gravity of, but there is a minor issue that makes this entry a little skeptical. The Prime Observatory room is where we got the mass of Zebes, and thankfully it provides the mass for Talon 4 as well. Prime's planet sits at 5.1 trillion teratons, which converts to 5.1 times 10 to the 27th power, or 5 octillion 100 septillion kilograms. The mass was a given, but the radius is where I encountered my first problem, the one I mentioned earlier. Only one of Talon 4's radii are given by Wikitroid, which means either one of the equatorial or polar radius is unknown. So until the other radius is known, I'm going to circumvent this problem by simply assuming Talon 4 is a sphere. However, chances are that's not the case, so take this calc with a grain of salt. At any rate, the known diameter for Talon 4 is 13,400 kilometers, so 13,400 over 2 gives us a radius of 6,700 kilometers, and assuming Talon 4 is a perfect sphere, the mean radius would be the same. Having the mass and radius of Talon 4, that leaves my calculation at 5 octillion 100 septillion over 5 septillion 972 sextillion 190 quintillion kilograms, divided by 6,700 over 6,367.43 squared, which becomes 853.95809577741 over 1.05222986354 squared, which is simplified to 853.95809577741 over 1.10718768573, which equals 771.285760111 Gs. Multiplying that by Earth's gravitational force leaves the number 771.285760111 times 9.802 meters per second squared, or 7,500.600.14302061 meters per second squared. For my sample, Samus would weigh 198 pounds times 771.285760111 G on Talon 4, or 152,714.580502 pounds. Dividing that by 2,000 puts Prime Samus at 76.357290251 tons. For reference, the world's largest fish, the whale shark, weighs up to 20 tons, barely over a fourth of Samus' weight on Talon 4. And Piranha Plant is heavier than her in Smash Bros. What a sick joke! I'm grouping all of these together because they all fall into the same line of reasoning, and ultimately, I gave all of them the same answer. I'll get to the crux of the argument here. We have no official numbers on any of these planets in mass or size. No observatory or wiki page is going to save me this time. Nonetheless, I think I have a suitable substitute for an answer until and unless official numbers are given for these planets. My reasoning for what the gravity of these planets could be is that Samus has the same in-game jump height that she had on Talon 4 throughout the Prime Trilogy. So the other planets in the trilogy, being Brio, Aether, Elysia, the Space Pirate Homeworld, and Phase, probably have just about the same gravity as Talon 4 does. All around these planets, but they sit at around 771 Gs, and by doing the equation 771 times 9.802 would put these planets at around 7,557.342 meters per second squared. You could argue that since Samus gets stronger over time, her jump height changes too, but whether her actual jumping capabilities increase or not during the Prime Trilogy is unknown, so for the purposes of this show, I'll assume it doesn't. You could also argue whether or not Samus retains her jump height on Alanos and Arctera, since it's hard to judge whether or not the jump on the small DS screen scales proportionately to the jump height of the games on the Wii, which share the same screen. However, I prefer having some sort of answer for what the gravity of these two Tetranian planets are, especially since it'd be really embarrassing if the prestigious Tetra Galaxy Telecast couldn't even comment on the nature of our premier places to stay. But anyway, I'm gonna count them here so that I can at least provide you, dear viewers, some idea of what the gravity might be, leaving them at around a nice 771 Gs. Now, we're almost ready to head back to the mainline entries, but for those keen viewers among you know, there's still one planet left to cover in the Prime trilogy. The question surrounding Dark Aether's gravity is whether or not it shares the same intra- and interplanetary forces as Aether, and the answer to that relies on if there are any differences between the dimensions the twin planets occupy. So I'm essentially answering a different question. Is the Dark Dimension from Metroid Prime 2 a clone of the normal Metroid universe, or is it simply a pocket dimension? I believe it's the former, and for a few key reasons. The first is that Dark Aether is stated, or at least very heavily implied, to be mimicking Aether's movements, which is why there are some objects in the game that have 50% of their atoms in one dimension and 50% to the other, but they both lie within the same space. What this means is that Dark Aether is copying Aether's movements. You could try to argue that the Dark Dimension is merely a copy of Aether's solar system, but you'd be remiss to do so, as Aether is actually stated to be a rogue planet, meaning it doesn't orbit a star, and more importantly, must be hurtling through space, flying about the final frontier unimpeded by other celestial bodies. Because of that fact, Dark Aether, in order to follow Aether's movements, has to have space to move around in. For that to be the case, Dark Aether has to be an alternate universe, and not a pocket dimension, because otherwise, Aether would have eventually flown out of the generated space of the Dark Dimension, given it had 50 years to do so, forbidding Dark Aether from mimicking its movements like the game shows it does. And since all of the universe's celestial bodies should be copied by the Dark Dimension, even the most minor gravitational manipulations should be emulated on the Ing homeworld. In short, it will have the same gravity as Aether, which, like mentioned before, could be placed at about 771 Gs and 7,557.342 meters per second squared. That just leaves us with these three planets for the Prime series. And sad to report, I have no way of measuring what the exact gravity for these three planets are. No specified size or mass is attached to them, so I can't directly calculate them, and Samus isn't even playable in the game, so I can't compare her jump height to that of other games. With those facts in mind, there's not really a way I can provide a definitive answer. All I can tell you is that these planets probably have a relatively low gravity for the franchise's standards. Seeing as the Federation force is able to leap similar bounds to what Samus can in the other Prime games, despite being weaker than Samus themselves and also wielding weaker technology, it could be concluded that what the Federation lacks next to Samus is made up for with the lower gravity of the Bermuda system worlds. I'm not confident in a hard number though. I'll slap out an estimate of 500 to 650 Gs so that we have a relatively rough idea of what it could be. Now let's move on to an answer that I've got a little more confidence in. So this one is a little more numbers based, but some speculation is still involved as SR388's size and mass are unknown. What I'm going to do is I'm going to measure how high Samus jumps in Metroid 2 with a basic spin jump, and I'll be comparing that to her spin jump's height in Super Metroid. How do I measure gravity using jump height, you ask? Well, remember that player's guide I mentioned earlier that had Samus weigh in at 198 pounds? Because that guide also states that she's 6 foot 3 inches tall. Using that, I can determine the height of her jumps by measuring her height when standing on the ground on my display module. Then, I can equivalize the height on the screen to 6 foot 3, before finishing the calc by dividing Samus's jump height over her standing height, and multiplying that answer by her height. To make this easier on myself, and for simplicity's sake, I'll quickly change the metric system, since that's mostly what I've been using anyway. And in doing so, 6 foot 3 comes out to be 190.5 centimeters. To give an example of what I'll be doing, let's say Samus measures out at 1 centimeter on my screen, and her basic spin jump caps out at 5 centimeters. I'll first divide 5 by 1, which of course gives 5. Then, since 1 centimeter is equal to 190.5 centimeters as that's Samus's game height versus her real height respectively, I'll multiply 5 by 190.5 to get the true jump height, which will be 952.5 centimeters in this example. Also worth noting, my display module may not be the same as yours, so the measurements might sound strange when you hear them. However, the proportions of all the elements of the game in relation to each other should remain unchanged, so none of the truly important numbers should be affected regardless of your visual terminal size. This is using the same assumption I made earlier with the Prime games that Samus's jump height doesn't change throughout the course of the series. You could argue that it does regarding games with longer time gaps like the Prime series, but considering how close Metroid 2 and Super Metroid are to each other chronologically, with Super starting mere minutes after Metroid 2 ends, her jump height should at least be the same between these games. A unique problem emerges, however. There are count them, two canon versions of Metroid 2. So unless the jump height retains its exact proportions in both versions, then I'll have to give two different numbers based on what each version shows height-wise. Now that that's out of the way, I'll start my measurements with Super Metroid, as that's what I'll be comparing SR388 to, and we already know Zebes' gravity. Samus, at 190.5 centimeters, stands at 1.5875 centimeters tall, and her basic spin jump reaches up to 5.3875 centimeters. Using this, I got 5.3875 over 1.5875 equals 3.3937007874. And since I'm equivalizing 1.5875 to 190.5, Samus' jump height here will be 190.5 times 3.3937007874 equals 646.5. Keep in mind that I use my own footage to figure these numbers out, so I can confirm to you that I did not press the run button when jumping here. I did not have any upgrades pertaining to jump height yet, as I just walked into the Bomb Chorizo room to collect the bombs. I measured a spin jump specifically, as the spin jump and straight jump have different heights, and I held the jump button to ensure that the jump was a complete jump, and not a partial jump like that of the so-called short hop. In short, Samus with no upgrades jumped 646.5 centimeters into the air with a basic spin jump on a planet with 1065.32485,173 times Earth's gravity. For SR388, I'll start with its debut game, Return of Samus. In this game, Samus stands at 2.1 centimeters, and can jump 5.2 centimeters into the air without any upgrades and a spin jump. It should be noted that the screen moves when you jump in Return of Samus, so to account for this, I measured one of the rocks on the landing site, which came out to 3.7 centimeters. After, I measured how high Samus jumped over the rock, and she got 1.5 centimeters over, so that's how I got 5.2 centimeters. 5.2 divided by 2.1 equals 2.47619047619, and since 2.1 centimeters equals 190.5 centimeters here, 190.5 times 2.47619047619 equals 472.44 centimeters. Having that information, I now have the means to find the gravity of SR388. Dear listeners, allow me to introduce a new equation to the equation. MAVA equals MBVB. This equation is often used when measuring molarities and volumes of a compound with strong acids versus a compound with strong bases during titration. It's known that MAVA equals MBVB because the values have to be equal when the two compounds have neutralized with each other after mixing, also called the equivalence point. For example, if 2 molar NaOH is mixed with 5 milliliters of 6 molar HCl, you could deduce how much NaOH you would need by doing MAVA equals MBVB. Since MA equals 6, VA equals 5, and MB equals 2, you'd have 2VB equals 5 times 6, which is simplified to 2VB equals 30, and then of course gives the answer of VB equals 15. So how does this pertain to the topic at hand? It does so because I can now use a custom version of the equation using the jump heights I discovered. GA equals GBHB, with G being the gravity and H being the jump height Samus has on the planet. Since I'm going off of the rule I established earlier that Samus' jump height won't change, this equation's equivalence point has been achieved, which allows me to use this equation. That makes finding the gravity from here easy, as it's simply GA times 471.714,285,714 equals 646.5 times 1065.324,85173, which simplifies to GA equals 688,732.516643 divided by 471.714,285,714, which can then be calculated to get our final answer. The gravity for SR388 in Return of Samus comes out to a staggering 1,460.06287599 Gs. Its gravity in terms of meters per second squared is that number multiplied by 9.802, which ends up at a ludicrous 14,311.5363104 meters per second squared. That said, you should be wary of using this calc. I'll explain why in a minute. SR388 is also the setting of Samus Returns, the 2017 remake for the 3DS, and there's good news and bad news with this one. I'll start with the good news. The calc itself is actually fairly easy. With all the preamble out of the way, I only need the numbers, and from my measurements, Samus is 3.33375 centimeters in height, and the peak of her base spin jump is 8.5725 centimeters from the ground. The screen moves when jumping in this game, but just like before, I measured a rock and compared her jump height to that, so this wasn't an issue. 8.5725 divided by 3.33375 equals 2.571428571443. And since 3.33375 centimeters equals 190.5 centimeters here, 2.571428571443 multiplied by 190.5 is going to give Samus a 489.857142857 centimeter jump. That makes the answer GA times 49.857142857 equals 646.5 times 1065.32485,173, which simplifies to GA equals 688,732.516643 over 489.857142857, which solves for a total of GA equals 1,405.98647,317 Gs, and a true gravity amount of that number times 9.802, which equals 13,781.47941 meters per second squared. That's when we reach the bad news. If you didn't notice by now, the gravity by calc is different between both versions of the game, which shouldn't be the case, as the planet in both games is the same. Specifically, these calcs of what should be a 1-to-1 ratio between the games actually ends up being a 1.03846153847 to 1 ratio in favor of the original. And considering how big the numbers I'm working with are here, that is a significant difference. I would advise remaining skeptical with these calcs, as having not been the same number, they really don't provide a true answer for SR388's gravity, though there are a few ways you could take this. You could take 1,460 Gs because that's the gravity of the original version. You could take 1,405 Gs because that's the gravity of the newer and more lore-focused version. Or you could take 1,433 Gs, as that's the mean between the two games. Personally, I'm inclined to go with the latter of these options, as it accounts for both of the Metroid 2s and gives us a nice rounded number of 1,433 Gs, which, let's be honest, rolls off the tongue much better than those other numbers, am I right? In any case, the inconsistency between games does mar the calc a bit, but until we have official numbers for SR388's size and mass, this is the closest we're gonna get. Since there are multiple potential answers, I won't be giving a sample weight. One last thing to mention, Wikitroid brings up that SR388 has a, quote, significantly greater crust than that of Zebes. Such a fact would give SR388 a much greater mass, so the fact that the gravity of SR388 ended up being significantly higher than Zebes checks out. That's all I have on the tale of two gravities though, so it's time to make the last, and very much hardest, calc of them all. The process here is very much like the one I used for SR388, just in a more roundabout way. So here's what I'm gonna do. I'm gonna measure the height of an upgraded spin jump in Super Metroid, meaning I'll have the high jump and space jump. Then compare it to the spin jump of the SAX, and using that to get the BSL station's gravity. Then I can get the height of a basic straight jump in Fusion, and then I'll measure that jump height and compare it to a basic straight jump in Dread to get the gravity of ZDR. To get the measurements I needed from Super, I went to Ridley's room with the high jump boots and space jump, as no one room can keep the camera locked for a full height Samus jump once upgraded. Thankfully though, Ridley's room provides repeating blocks of the same size across its walls. There's also a doorway, but I measured that too, so that shouldn't be a problem. Each block was 1.016 centimeters, and she fully scaled 6 of them. The doorway was 5.588 centimeters, and the last block reach was only partially cleared by Samus, as she gained another 0.396875 centimeters of air in the process. Adding these together, she jumps 6.096 plus 5.588 plus 0.396875, or 12.080875 centimeters. since 1.5875 equals 190.5, and Samus jumps 12.080875 over 1.5875, or 7.61 times her height, 190.5 times 7.61 is equal to 1,449.705 centimeters, meaning Samus can jump 1,449.705 centimeters with space jump and high jump equipped in Super Metroid. It's now time to measure the SAX, and let me tell you, she was a pain in my side right from the start. Not only does the SAX only do spin jumps, which is why I was measuring in spin jumps in the first place, its jump height is only reliably measurable in one cutscene since you can't play as her and thus control her jumps. And what's worse, the peak of her jump in that one cutscene is obscured by the top of the elevator. I thought I was doomed this time, but fortunately, the sprites of her jump animation are reused, so I was able to measure how tall she is during her jump animation, then measure from the top of the SAX when standing on the ground to the bottom of her peak jump height, then add the SAX's height during the jump animation to her standing height and the aforementioned distance. In doing this, I found the SAX reaches 4.7625 centimeters off the ground, while having a standing height of 2.5 centimeters. You know the drill by now. 4.7625 divided by 2.5 equals 1.905, 2.5 equals 190.5, and 1.905 times 190.5 equals 362.9025 centimeters. That means the GAHA equals GBHB equation will be 1,449.705 times 1,065.32485,173 equals 362.9025 times GB, which simplifies to GB equals 1,544,406.76418 divided by 362.9025, which ends up giving us the value of GB, which sits at 4,255.70715,049 Gs, which is also that number times 9.802, which equals 41,714.4414891 meters per second squared. With the SAX out of the way, I can now compare the jump heights using a straight jump. For base Fusion Samus, she stands at 1.74625 centimeters and jumps 4.60375 centimeters on my visual module, 4.60375 over 1.74625 equals 2.63 unending, and 1.74625 centimeters equals 190.5 centimeters. So 190.5 times 2.63636363 etc. equals 502.272727 etc. In Dread, Samus's jump is 6.82625 centimeters, and her height is 2.38125 centimeters. 6.82625 divided by 2.38125 equals 2.86 unending, and 2.38125 centimeters equals 190.5 centimeters. So 190.5 times 2.8666666 etc. equals 546.100000001 centimeters. Assuming Samus retains her jump height, she jumps 546.100000001 divided by 502.272727 etc. centimeters, which is 1.08725791855 times higher than her fusion self. That would make the gravity of ZDR the reciprocal of that value, or 1 over 1.08725791855, which equals 0.919744968845 times the gravity of the BSL station. So, 4,255.70715,049 times 0.919744968845 equals 3,914.165,23886 Gs. That times 9.802 equals 38,366.6476713 meters per second squared. These results are also quite speculative, however, because you would just as easily argue that the BSL station's gravity is equal to SR388. Sector 1 is stated to be a perfect recreation of the planet's environment, so it could be argued that surface gravity would naturally be a part of that recreation process, and since the jump height remains the same in the other sectors, they share the gravity as well. That would put ZDR's gravity somewhere around the 1,295 to 1,345 range. Sadly, neither of these ways to obtain ZDR's gravity are definitive answers, and should be considered void should official numbers be given for the BSL station or ZDR's gravity, but I believe that one of these numbers should be a satisfactory answer until that happens, even if the former of these counts is quite high, even for Metroid standards. Of course, much like SR388, due to having multiple possible answers, I won't be giving a sample weight. And that was a look at the gravity of planets in the Metroid franchise. Do you have any objections to the answers I've provided? Maybe the Bermuda system is too low in your eyes, or maybe the BSL station and ZDR are way too high. Perhaps you agree with Wikitroid's 954G stat as opposed to my own. Does it even make sense to you that Samus and the Space Pirates can duke it out on such gravitationally intense worlds? Of course, I did skip over other settings in the series, like Ormine and Jagrod, among others. If you would like me to make a follow-up to this telecast covering those and other as-yet undiscussed areas in their franchise, or if there's anything else in your mind that you'd like me to hear, feel free to say so in the digital reply box down below. Station feedback is very much appreciated, as it will continue to help this channel grow and, more importantly, improve with time. That will be all for today's transmission, though. I hope you learned something interesting today. Thank you all for tuning in, and I'll see you next broadcast.